Welcome to G Fun Facts Online. Imagine holding a rock that's billions of years old. It seems silent, lifeless. But what if I told you that rock is whispering a story? A story about the very origins of life, the air we breathe, and how our planet became a home. Today, we're becoming geological detectives because deep within these ancient stones, scientists are decoding a chemical secret that's completely rewriting the history of Earth. So what's this big secret about? It all comes down to one element: nitrogen. You might know it as the most common gas in our atmosphere. But here's the catch. That atmospheric nitrogen is like a locked treasure chest. Most life can't use it directly. To build the essentials, like proteins and DNA, life needs nitrogen in a fixed or usable form. The process of converting atmospheric nitrogen into this usable form is called nitrogen fixation, and it's one of the absolute cornerstones of life. Figuring out when this process started is like finding chapter 1 in the story of life on Earth. How on earth do you find evidence of a chemical process from billions of years ago? The answer is incredibly clever. It lies in a kind of atomic fingerprint. You see, not all nitrogen atoms are the same. There's a common, lighter version called nitrogen-14, and a slightly heavier, rarer version, nitrogen-15. When living things, like ancient microbes, use nitrogen, they often show a preference for the lighter one. This leaves behind a distinct ratio of heavy to light nitrogen in the environment. This ratio, this isotopic fingerprint, gets trapped in sediments that eventually become rock. By analyzing this fingerprint in rocks that are billions of years old, scientists can tell what kind of life was active back then. Of course, it's not that simple. Reading a 3-billion-year-old message comes with challenges. Most of these ancient rocks have been baked, squeezed, and transformed by immense heat and pressure over eons. This process, called metamorphism, can smudge or even erase the original chemical fingerprint. It's like trying to read a letter that's been left out in the rain for centuries. But scientists are smart. They've developed complex models that act like a digital restoration tool, allowing them to calculate what the fingerprint looked like before all that geological chaos, peeling back the layers of time to reveal the original secret. And the secrets they're uncovering are staggering. Let's start with one of the biggest events in Earth's history, the Great Oxidation Event, around 2.4 billion years ago. This is when oxygen first started filling our atmosphere, paving the way for complex life like us. The classic story was that life started using oxygen, and then the atmosphere filled up with it. But recent analysis of nitrogen isotopes from ancient rocks in South Africa tells a new story. It suggests that microbes in the ocean were already using oxygen-dependent nitrogen cycles about 100 million years before the atmosphere became oxygen-rich. There was a huge delay. The oceans had pockets of oxygen long before the air did, giving life a head start to adapt. But we can go back even further. By looking at 3.7 billion-year-old rocks from Greenland, some of the oldest on Earth, scientists found isotopic hints of biological nitrogen fixation. That's life, actively shaping its environment almost 4 billion years ago. But they also found something else. Some fingerprints were unusually light. This led to a wild hypothesis. Maybe it wasn't just life. In Earth's chaotic early days, maybe the sheer energy from constant lightning strikes was powerful enough to split nitrogen atoms in the atmosphere, creating a non-biological source of fixed nitrogen for early life to use. This completely changes the picture of early Earth. For a long time, we thought early life was constantly struggling, limited by a scarcity of usable nitrogen. But more new research, this time on 2.7 billion-year-old fossilized microbial mats from Zimbabwe, adds another twist. These ancient microbes weren't just pulling nitrogen from the air. They were also slurping up ammonium that was bubbling up from hydrothermal vents on the seafloor. This means nitrogen was actually more abundant in the early oceans than we ever imagined, allowing life to thrive in both deep and shallow water. long before our atmosphere was breathable. So these geochemical timekeepers, these tiny isotopic fingerprints in ancient rocks, are showing us a more dynamic and resourceful early Earth than we ever knew. The story of life isn't just about a struggle for scarce resources. It's also a story of adaptation and of a planet that provided for life in surprising ways, from lightning in the sky to vents on the ocean floor. This doesn't just rewrite our own planet's history, it gives us a new blueprint for what to look for when we search for life on other worlds. The rocks are still whispering their secrets, and we are finally learning how to listen. Thanks for tuning in to G Fun Facts Online. What ancient mystery do you think we'll solve next?